From ContainerDays Hamburg, this video is proudly presented by Dux IT.
All right, you are on the right track, which is about traffic engineering Kubernetes. And as I mentioned, I will try to be concise but informative in this topic. We will spend some time to discuss it, but before we go on, let me introduce myself. I am a senior customer success architect at Isovalent. My career path has been traffic engineered by different events and decisions, not only mine, but also other companies. So Isovalent has been acquired by Cisco, and my colleagues from Cisco, because I worked for Cisco for 7 years before, are laughing that Cisco acquired Isovalent because of me, which is not true, of course. They acquired because of eBPF, because of a great product, and I, of course, advise you to test it before using. And what's more, I have a couple of interesting stuff, certifications, and in free time I like rowing on my rowing machine. This is keeping you busy and a bit healthy, at least in my consciousness. What is our journey in this session, during this session? We need to divide traffic engineering into some chapters when the traffic is flowing through some stages of the topology. So we will get on board and we will see how the Kubernetes inbound traffic looks like, outbound routing protocols, and traffic engineering matrix as a summary of the flows we can find out in the cluster. But before going there, we can consider what is the purpose of making traffic engineering matrix or finding out how the traffic engineering pattern looks like. And we can consider that based on the tube map from 1920 created by MacDonald Gills, tube map from London, and it looked like this. It's nice, isn't it? But it's quite condensed in terms of stations, lines. Is it easy to read? Not really, because it's, again, congested. And how we can solve that, how we can improve here. Probably you know, if you've been to London, a bit different map, which is created by Harry Beck in 1933. Of course, since then, the map evaluated a bit, but look at the difference here. The idea here is that we abandoned, Harry actually abandoned the idea of synchronization between the line, tube underground lines with the geographical location. So the central London is stretched a bit, making more space for different shapes of lines, which makes them easier to read. Why I'm saying about this? Because the same for Kubernetes. Kubernetes is tangled environment, it's a microcosmos environment. My background is networking and security. But when I entered the space of Kubernetes, I needed to learn about storage, I needed to learn about compute. If I'm doing troubleshooting of etcd KV store, I need to know a bit about storage, about not only just about networking, I need to know about how to allocate resources, how these resources are used. And the same with traffic engineering. Traffic engineering in Kubernetes requires some clarification. So my purpose here also during this session is to find out, to give you also some simpler representation of understanding how the traffic flows to and from Kubernetes clusters. Before going further, let's do some naming conventions and have a better common understanding of some terms which I will use interchangeably, like flows. You can have unidirectional and bidirectional flows. Flows which are coming or which are initialized from external network, as well as initialized from internal network, internal from Kubernetes point of view. This is very important because, you know, the way how you configure other stuff like stateful firewalls, the way how you expose applications, all this matters in terms of who is initializing the traffic first. And also in terms of ingress and inbound. Ingress is a term which is a bit confusing because you can describe the inbound traffic by ingress, but also ingress is the Kubernetes resource which manages HTTP traffic inside to the Kubernetes and propagates the traffic through two different pods. And also egress, we have a meaning of outbound traffic from pods to the external networks. So let's go through some concepts to clarify them step by step. First of all, let's start from inbound traffic, because this is the majority of use cases for Kubernetes. We would like to expose application externally, like e-commerce shop is exposing application to clients in the internet. Inbound traffic is going in, and we can take care of this traffic through the load balancing services like ingress or gateway API, or maybe service mesh entry, service entry, something like this. And then we distribute the traffic to the nodes, to the backend nodes. Essentially, there are two major algorithms or strategies called external traffic policy, which can be tied to the service. So we can have cluster or local. There are three characteristics each of them have. And I will, of course, list them all. Let's start from the first characteristic. The first characteristic is that service external traffic policy cluster unconditionally advertises IP address related to service A in this case through any node, regardless whether there is a backend pod or not. So as you can see, the traffic is attracted to service A to both nodes, even though the node number 2 is not having any pod related to service A. There's just one backend pod. Of course, this is just a simplistic example, but this is how the cluster works. External traffic policy cluster. So what is the difference comparing to external traffic policy local? In this case, the IP address is advertised only when there is a backend pod existing in the node, on the node. So the traffic is coming in just to the nodes with the backend pods for the specific service. What else? What is the second characteristic? The second characteristic is that for external traffic policy cluster, we have both destination and source NAT from the external network perspective. Why like that? Because we need to provide a symmetrical routing, symmetrical path for the return traffic. Why? Because once the packet is coming in to the node number 3, and there is a translation of destination IP address and the source, then the packet is reaching port number 3, then the return traffic is sent back to the same node, then we can expect the proper reverse NAT. So destination NAT and SNAT creates entries in the contract table, and return packet can be properly translated. If we don't do, let's say, SNAT, the port number 3 will try to route the traffic directly through the interface related to the node and reach the destination, which is a failure because the traffic must be translated. Why? Because the pod is having, let's say, private IP address, and this traffic must pass the translator, and the translator is here, not in the other place. So again, we need to provide here not asymmetric traffic, but symmetry between the traffic coming in and out. Whoa. So what's the difference then with the other external traffic policy local? We will see in a second, but there is a third characteristic before going that. The first characteristic is that the load balancing ETP cluster is doing traffic engineering and distribution of the traffic per pod. To visualize this, I added traffic load on the slide. So I used just the number 9, artificial number 9, for a better calculations, because then I have 3 lines, so this will be a better distribution without fractions. So then 9 traffic loads units will be distributed with 3 traffic load units per each line. So we will end up in a situation that each pod will take 3 traffic load distribution units of the load. So this makes the load balancing, in this case, equal per pod, not per node. Why not per node? Because let's say on the node number 2, we have 2 pods, and the overall traffic which is coming to the node number 2 is equal to 7 traffic load units. And 1 traffic load units is passing through the different pod through this node number 2. Why I'm discussing about this? Because you can make a decision about your strategy of load balancing based on your fleet of nodes in the cluster, or how you spread your application through the clusters, through the nodes composing the cluster. If you would like to have an equal load balancing per pod, you can use this strategy. In comparison, in the ETP local strategy, first of all, we just do destination NAT, but client's IP, source IP is preserved. Why? Because we can conserve the performance. We don't need do the source NAT, because there is no option that return traffic from pod number 2 will cross the line between the node number 2 and node number 1. So the return path is always going through the contract table on the same node. So thanks to that, the client IP can be preserved. What about the similar concept of traffic load? Here we have a load distribution per node. So the same traffic load units we have per node, which is in this case 4, because I use just number 8 as an entry level of traffic load. And node number 2 is having the same traffic load, but each pod is having a fraction of this traffic load, because the traffic is splitted on the pods existing on this particular node. If we have 4 pods, on node number 2, what will be the traffic load per pod on number 2? 1, just 1, very good, yes. Based on that, we can create, or we can resolve some issues which are real requests from the customers. So recently, we had a discussion about the real deployment of Kubernetes cluster composed of 1,000 plus nodes. And the customer would like to get rid of a situation, or they are considering how to scale out BGP sessions or advertisement of prefixes, because if each node or some of the nodes are having the pods inside on board, how we can set up the connectivity with the external network using BGP, because we would like to avoid the situation that BGP session must be established with every node, because it's not scalable. So what we can do with that? Can we use external traffic policy local? Maybe in this case, yes, if we have just 3 nodes, because each node is having the pod. And as we remember, ETP local means we advertise IP only when the pod is existing there. But what if other nodes are not having such pod? We will have a black hole of the traffic. So how can we solve this topology? How can we solve the solution? You can use such solution like here, where when you have the front end of nodes establishing connectivity through the BGP, and you have the external traffic policy cluster, even without pods, the IP address will be advertised because, as I mentioned, the unconditional advertisement of IP related to the service. And then the traffic will be equally distributed to pods existing in the backend nodes. So this is the approach where when you can combine your knowledge and combine the strategy of load balancing the traffic with efficient architecture. And then we can move on to outbound traffic. So outbound traffic is the traffic which is initialized from inside of the Kubernetes environment to the external network. In this case, there are different challenges and problem statements to resolve, because why we need to do anything with this traffic? Cannot just this traffic leave out and reach the destination? Not necessarily, because the security perimeter must, for example, inspect the traffic, let's say stateful firewall. How do you know which application is leaving the Kubernetes cluster on the best next generation firewall? Next generation firewall doesn't have the context of Kubernetes. How do you identify the application? The only way to identify the application is through the IP address. So you need to have deterministic IP address. And for that purpose, you can use a function which is called egress gateway. Of course, as a representative of Isovalent, I'm presenting you functions which are used by Cilium, but please do not stick to this term egress gateway or Cilium functions. Just take the functional view of this feature or this component, because of course you can find on the market equivalent products as well. So that's the disclaimer. So egress gateway, what is doing allocation of IP address for the application. We can allocate, let's say, IP address like 20.0.0.1 for a specific pod or specific group of applications which will be leaving the cluster through the gateway to reach the destination. And we can do this allocation of IP address per application, per destination. So we can create this association quite in a granular way, granular fashion. So you can better control who is exiting your cluster. Why? Because then on the firewall you can create exact policy saying, yeah, IP address 20.0.0.1 has the access to the SQL database. That's it. And you can get this access to the SQL database. But other pod which will be existing here will get a standard different IP address which will identify less prioritized traffic or general traffic which can access the internet, but not the critical services, legacy services or databases in our organization. So that's the use case which is behind egress gateway. And this is kind of also traffic engineering. Why? Because again, we are forcing the traffic within the Kubernetes cluster to reach the egress gateway via VXLAN tunnel. Otherwise, the traffic will leave this interface ETH0 directly to the external network without going through the proxy gateway node. So this is kind of traffic engineering as well. Other part of traffic engineering is how we can make this solution more cost-effective. Why? Because let's imagine you have a cluster in the AWS environment where the pod is hosted on the AZ availability zone 1, and there is other availability zone, let's say west, east-west. Then you would like to avoid cross availability zone charges for the traffic which is leaving availability zone east and is going through the availability zone west, through the gateway which is living here. To make this routing decision going outside, pushing the traffic outside based on the availability zone, you can add the affinity bit, affinity keyword like local only first. This is the example where the local gateways will be chosen as first choice to exit the specific availability zone. So in that case, you can reduce significantly cost for cross-availability zone charges, cross-availability zone traffic. And you can find more such keywords which can help you out to decide which strategy to choose. You can choose local only, you can choose local only first. There is also local priority, and based on that, your strategy can be not only related to the Kubernetes, but also can affect optimizations related to the cost and business wide stakeholders in your company. So to summarize ingress and egress traffic, we can have such a picture like this, which is aggregating all the north-south traffic. This is quite a condensed representation, but it shows at different flavors what can happen with the application. For example, application A is just exposing the traffic, it's exposing application to the external traffic, which is coming in. It means that initialized traffic is from the external network to the inside of the Kubernetes. But application B, which is the green one, can use both. Can use ingress services for the traffic coming in via node number 2, but also can initialize the traffic through the egress gateway. Can this IP address of service B and egress gateway be the same IP address? Yes, it's possible, but please note that unless the traffic is initialized through the egress gateway, any traffic which is trying to reach the egress gateway here will be unsuccessful. Why? Because this behaves like a network address translation in one way. The connectivity must be established before the return traffic can be allowed on this function. So it's a bit complicated. Who can initialize the traffic where? So to summarize again, service A to service B to application C, the traffic can be initialized from external network if we advertised these IP addresses externally, if we made them reachable for other entities. Whereas egress gateway, the traffic must be initialized from inside of the Kubernetes environment. Routing protocols. We need routing protocols to make these IP addresses reachable from external network. Static routing is the simplest representation, and in some way it's a good enough solution because from Kubernetes side we need just default route, and static routing from upstream devices, it's also a viable solution. Why? Because we can combine it with BFD. I'm using some acronyms which are standard for networking, guys, but if you don't know it, BFD is bidirectional forwarding detection, which is simply kind of probing. So this device can send probes to check if the gateway is still alive. So simple as that. And if there is no alive gateway, the static entry is removed. So the static routing can be nowadays quite dynamic if you combine it with probing. But more scalable solution we use with our customers are based on BGP, and BGP is the protocol you can establish between not only Cilium but also other vendors on the market, of course. So again, this is solution available on the market for Kubernetes already. You can also establish BGP session using FRR or Linux instantiation of BGP as well. So simply, the task is to advertise prefixes dynamically. Why dynamically? Because again, if this pod is no longer on this host, the traffic shouldn't be directed maybe through this link. It should be directed via bottom link to make this more optimized, cost-effective, and to avoid black holing. More complicated policy you can create with BGP is based on some attributes like community or AS path. So by default, BGP diverts the traffic through the shortest path. How the shortest path is calculated? Shortest path is calculated not based on the hops counted by how many devices the traffic passed, but by the autonomous system numbers the traffic actually need to pass. So you can compose your environment into groups, so into some enclaves. You can have one group, and there will be one autonomous system. Then you can have other autonomous system, third autonomous system, and so on. So less autonomous system means shorter path. And in that way, from that perspective, you can also manipulate AS path by prepending. Prepending means adding artificially additional autonomous system to make the AS path longer. In that way, this router number 4, will make a decision to divert the traffic through router 3, then route reflector 1, and then to the host located in availability zone east, not the bottom one. So further from the Kubernetes, more classical networking comes into play. If you don't want to be engaged into the classical networking, of course, stay focused on the Kubernetes, advertise your prefixes, and let networking guys know that this is done. Okay, that's fine. If you want to be involved with the traffic engineering end-to-end, unfortunately, you need to be also involved in the classical networking stuff, including BGP. But making you more aware, you can, or by creating a representation of your traffic flows coming into your application and going out, you can better understand if you have, for example, the task to profile performance of your application. You can better understand how the traffic path affects your performance of the application. If your clients are complaining about the performance, you can measure what is the latency of this link. Maybe this link contributes to the latency higher than the bottom link, and yeah, you can divert the traffic through the bottom link and then resolve the issue with the other part of the infrastructure, or give the networking guys let them know that there is an issue with this topology. But if you are trying to understand what is happening end-to-end, please know that one of the dangerous situations is the traffic asymmetry. Of course, in the internet, traffic asymmetry is a common thing, but here traffic engineering might be useful to avoid traffic asymmetry. Why? Because if you have firewall, like in this situation, 2 firewalls which are operating separately, what can happen? You can have a traffic discarded. Why? Because, again, traffic going out didn't create a necessary connection in the connection tracking table, or a stateful state of an entry of the connection existing in the bottom firewall. So when the traffic is choosing the path through the bottom firewall doesn't know anything about this path, about this flow, and it simply drops the traffic. How you can solve this situation? There are two solutions, at least. You can either provide exactly traffic engineering path through the firewall, top firewall, or create a cluster of firewalls which makes all the entries synchronized between two members of the firewall cluster. So in that way, you can consider step by step what parts of the network can contribute to the performance of your application, because it's not just the Kubernetes. Of course, if you are just responsible for Kubernetes, you will be not involved in BGP policies or how the paths are distributed. But if you are interested into that topic, you possibly need to know that, first of all, if you would like to do the traffic engineering, you need to provide some choice. If the core network is sending just one path to the Kubernetes cluster, that means that the external network entities don't have the choice to do the traffic engineering. What does it mean? It means that you need to provide some path diversity. In each picture which I presented to you, we had such a path diversity. We have a choice. One link, another link, bottom link, up link, link to availability zone east and availability zone west. We always need to give the choice to provide traffic engineering. How we can provide traffic engineering path diversity in the classical networking using BGP? There are some concepts and acronyms listed here, like shadow route reflector, shadow session, add path, unique RD. If you are more interested into that, please reach out to me after the session. But that's the common concepts which are needed to be used here. All right, to slow down a bit, because we are close to the end of the session, I encourage you to have a look on your overall topology, not just traffic engineering related to the Kubernetes, but overall as extended topology as possible, to better understand what are the services used for the particular directions of the traffic. And for example, here we have traffic engineering matrix, which summarizes two basic bidirectional flows. One flow which is yellow, which is initialized from the external network to the Kubernetes, to the ingress services. Initial site is external network. Then we have some steering methods. This is the example how you can create a review of your network, maybe not alone, maybe with other departments, to again better understand the influence of each decision, routing decision on your application, because this decision can be can include performance, but it can include also packet drop. The bottom flow, which is green one, is initialized from the Kubernetes to the external network, and here we have a return path going from external network to Kubernetes. And the services used for that purpose are different than for the flow initialized externally to the Kubernetes. Again, building awareness about it is useful to understand which components need to be tweaked or tuned to achieve better performance. Maybe, again, not only performance, but cost optimization, or proper direction to the traffic to the node. That concludes my session, and if you have any questions, I'm happy to answer. What is the default way egress works in Cilium? If we don't use egress gateway, the default egress is through the main interface of the worker. So it depends how we configure egress. If we configure masquerade, the traffic will be translated. If no masquerade, the traffic won't be translated. But of course, egress gateway is optional component.
What is needed in an on-prem network for BGP as compared to simple app?
What is needed in on-prem network for a BGP? In on-prem network for BGP, we need just an instance of something which can instantiate, which can establish BGP session. So please remember that we can establish the BGP session multi-hop. So if you have a on-prem instance, you can establish a multi-hop BGP session even to the Kubernetes, which is in the cloud. But all the components in between must also be aware how to reach source and destination prefix.
Thank you. The next question is, can Cilium replace also MetalLB Cube VIP in an on-prem network?
Yes, if you can instantiate Cilium on the host on-prem, yes. How do you overcome the BGP maximum path, which is 1664, depending on the vendor? For example, through the layered design, which I presented to you. So through having the first layer of nodes, which are establishing sessions to the external network. Let's say you can have 8, 10, 12, whatever, up to the limit of ECMP. Then you can have a route reflector function, and then the backend nodes of Cilium, where the traffic will be distributed. What is interesting from V1.18, route reflector is also in Cilium. So you can have this route reflector function as the Cilium function or the other external function. Can we have the slides? Absolutely, yes.
They will be shared afterwards, but if people follow you on LinkedIn, they probably will you post them?
How can I post? Okay, anyone who would like to have slides, please reach out to me after the session straight away in the booth. I will leave the link to how to download the slides. Okay.
Perfect. Thank you.
If we have an ingress controller with host network true, how does this affect and play together with the external traffic policy setting? Yeah, true. It's if you have ingress controller with host network true.
And also deep dive with the one who asked the question.
Yeah, let's take it offline. The last one, are there also CNIs LBs using OSPF or ISAs? I'm not aware of that, but they won't be so scalable comparing to BGP. So typically OSPF and ISIS have a different purpose in data center or large network than BGP, and for the number of prefixes we have in data center, it would be less advisable to use OSPF and ISIS. All right.
Thanks for answering all the questions again, and thanks for the great session.
Thank you.
From ContainerDays Hamburg, this video is proudly presented by DAX IT.